in your flow, you also get turbulence. Okay, so here are some examples of fields that utilize turbulence in their studies. So you could look at hydrodynamics, you could look at aerodynamics, external aerodynamics, also atmospheric flows. A lot of geological flows and planetary flows are highly turbulent, so that's relevant there. And then, as I mentioned, biological flows also exhibit turbulence in some cases. So 25% of the energy used by industry is spent in moving fluids, either moving fluids or moving objects through fluids. So it's a significant portion of the energy used by industry. And out of that, 25% of the energy is dissipated close to the wall. So walls play a big role when it comes to moving fluids around. So wall-bounded turbulence is responsible for about 5% of the CO2 that's dumped into the atmosphere every year. And on top of all those kind of practical reasons of understanding and studying turbulence, Richard Feynman famously said that turbulence is the most important unsolved problem of classical physics. So that gives us kind of a reason to study this phenomenon as a whole. And one example that I'm actually going to talk about today in terms of why we want to use models in turbulence is because to do something like this. So, when we have an aircraft, a lot of the times, the aircraft needs to be certified, right? So it needs to be made sure that it's safe to fly. And for that, it takes a really long time to get through the certification process. So for example, in the case of Boeing 787, it took about 8 years from application to certification. So this was, after all the design process and all that, it took extra 8 years for this plane to be certified. It took numerous hours in terms of flight testing, numerous hours in terms of, the FAA's time to certify this, and over $100 million in terms of certifying. So now there's a lot of push towards this idea of certification by analysis. And this is the idea where we can use analysis-based means of compliance of airplane and engine certification. So, part of it is using simulations to hopefully, aid in the certification process. It wouldn't replace all the flight tests, but it could potentially cut down a lot of the time and effort going into the certification process by replacing some of the parts through both wind tunnel experiments and CFD experiments. But the idea is to do that. And for that, we need more accurate CFD models. So here is a chart. Take this with a grain of salt, because this has been published by Star CCM, which is a CFD company. But the idea is that, CFD has a much lower model cost than, wind tunnel experiments, obviously a lot less than a flight experiment would actually cost. And in terms of, how fast you can run these things, it's also quite efficient. So this is, again, one of the reasons that there's a push towards certification by analysis. However, the problem with simulating these very complex flows over, airplanes, again, airplanes are traveling at a very high speed, they're very large, and air is the viscosity of air is very low, meaning that it contributes towards very high Reynolds numbers. So again, because Reynolds number means the ratio of the large scale and small scale motions, this means that there's a big scale separation between these two scales. So here's a plot of how these two length scales change as a distance away from the wall. So in this plot, I have on the x-axis the distance away from the wall, which you could think of as like an airplane wing, let's say. And in the red is the shear length scale, which represents the large scale motions. And in black is the dissipation length scale that represents the small scale motions. And as you can see, that the large scales, they start growing away from the wall. And then the small scales, they stay more or less very similar throughout the full region. So if you study wall-bounded turbulence, you'll see that you have a very fine scale that doesn't grow as fast away from the wall, and a large scale that grows quite fast away from the wall. So if you want to simulate a high Reynolds number flow, in order to capture all of the physics that is present in the turbulent flow, you need a domain size that is large enough to capture your large scale motions. And then a grid that is fine enough to capture all of your small scale motions. So for a direct numerical simulation where you resolve all these scales, you would need a grid that looks like this, where basically you have fine resolution everywhere. And this is a very costly, and in particular, the cost of a simulation for high Reynolds number flow grows as a order of Reynolds number to the 2.6 power. Now, in practical terms, what this means is that if you want to simulate an aircraft that you see on the right here, it would take on the order of 100 years, basically, to run any simulation to completion. So that's not feasible. And that would be using the largest supercomputer that exists right now. So what a lot of people do is they look at, these two length scales and say, can we find a way to, not have to have these super fine grids everywhere? And one way to do that is to take these small scales away from the wall and model them, because these are kind of they're ubiquitous. They're in a way they're very amenable to modeling, because they behave kind of similarly everywhere. So when you model this is called large eddy simulation, or wall resolved large eddy simulation. And in this case, close to the wall, you would need very fine resolution. But as you go farther away from the wall, you can get away with coarse grids because you're modeling the small scales. Still, this is quite expensive. It's almost Reynolds number to the power of 2. It's achievable. So in this case, running a simulation would take maybe months or on the order of years. But still, for it to be feasible tool for design process and certification, this is still not good enough. So then and one of the reasons was because that you have these very fine scales close to the wall. So the final step in the modeling process is to look at this close near wall region and basically say, can we model this part as well? Because if we can model this part, what we can do is we can have a very coarse grid everywhere, and this would be at most linearly, the cost grows linearly with Reynolds number. So this, would allow simulations like what you see here on the right. So this is a simulation of a NASA high lift configuration, and you can see kind of, there are very diverse physics that is going on in this flow. But the way this simulation was done was using wall modeled LES. That was this last example here. And basically this took maybe, one day or a bit less using a reasonably sized supercomputer. So this is kind of where we want to be in terms of being able to simulate very high Reynolds number flows. So again, this is kind of why we're interested in these models, because the more accurate your model, the more accurate your simulation is going to be. So this is what wall modeled LES is kind of in a nutshell. So the idea is to bypass the near wall physics and supply the wall shear stress directly, so that the model basically takes care of this very fine region close to the wall and just supplies the necessary information. And practically how that's done is that you have a coarse simulation grid. You take some flow information away from the wall, either 1, 2, or 3 cells away from the wall. That could include some velocity information, velocity gradient information, any other sort of information you need from the flow. You plug that into the wall model. And the wall model will give you what's called the wall shear stress, and this is the most important quantity to make sure that the statistics of your flow are correct. So you take the wall shear stress that the wall model gives you, and then you apply that as a boundary condition, rather than applying a typical no-slip boundary condition for the wall. So this is kind of the schematic of the wall modeled LES. In terms of what's being used now for these very complex flows, and for example, that aircraft that you saw earlier, is something called either the algebraic wall model or a RANS-based wall model, or more commonly known as the equilibrium wall model. So both of these utilize what's called this law of the wall. And what the law of the wall states is that here in this plot, you have on the y-axis velocity, and on the x-axis distance to the wall. And regardless of Reynolds number, you can collapse the mean velocity profile of a turbulent wall-bounded flow onto this red line. This is only for the case where you have a zero pressure gradient over the surface. But nonetheless, this is a very powerful law because it doesn't matter whether you have Reynolds number of 1,000, 10,000, or 1,000,000, you would be able to collapse part of your mean velocity profile onto this red line. So the current wall models utilize this fact. The algebraic wall models, which are a simpler version of this, basically says we want to make sure that the mean velocity profile is on this blue line. And because in wall model LES, typically we have coarse grids, it tends to be correct. The RANS-based model goes one step further and say we want to make sure that the velocity is on this red curve. And this involves solving a ODE at each computational grid point, and basically solving for the wall shear stress that would make sure that your velocity instantaneously lies on this red curve. So that's kind of the idea of these wall models. Now, what is the problem with using this model? Like I said, this red line only holds if you have a zero pressure gradient. Now, if you have an aircraft, that's actually not true because you have pressure gradient effects, you have separation, you have a lot more complex physics going on such that you cannot assume this red line holds anymore. So here's, for example, a flow, adverse pressure gradient flow. So this could be something you see on near the trailing edge of an aircraft. And you'll see that flow starts deviating from what is typically a zero pressure gradient flow. And you can see it even further in this plot on the right, where you see for this red case where you have a zero pressure gradient, the mean velocity profile lies on this dashed line, which is the log law or the law of the wall. And as you start increasing your pressure gradient, you see deviations happening. So in this case, basically, you cannot use the current wall models and expect to get good results. So that's kind of the issue here. And in this case, wall models would need to be recalibrated for all values of the pressure gradient, which is just not feasible. So again, that's kind of why the current wall models are an issue. Another example of when the current wall models won't work is when you have flow over rough surfaces. So again, rough walls act similarly to pressure gradients, where if you start having more and more roughness, your mean velocity profile will start deviating from the law of the wall. So again, in this case, you wouldn't expect good results by using the current state of the art models. Still, it's being used quite a bit. Being used quite a bit, and there are limited successes, but it is what is most widely used in the current field at the moment. So there has been some efforts towards using supervised learning in wall modeling, and for a flat plate zero pressure gradient case, it has been quite successful. So you can see here they've gone up to extremely high Reynolds numbers, and you can see that it matches the law of the wall very well. And again, this law of the wall you can actually get with this state-of-the-art model. So technically there was no need for learning this model, but this is just a demonstration that it could work. The only problem with supervised learning is that, you know, you need a lot of data. You know, in order to run this, you know, there's a lot of data for zero pressure gradient flows, because that's the most canonical case that people have studied for decades at this point. So there's a lot of data out there for this type of flow that we don't really need to model. But there isn't a lot of databases that you know, deal with pressure gradient flows. And in particular, supervised learning actually needs, you know, full flow fields, not just statistics, which means it's very, very much not data efficient. The other part is that there's a very big difference between doing LES and DNS. So remember, DNS was when you resolve all scales of motion. LES is when you model small scales. But on top of that, you also have a very coarse grid, which means that between LES and DNS, there's no direct mapping that will allow you to say, oh, convert this DNS flow field into a wall-modeled LES flow field equivalent. And because of that, even though these supervised learning models do well a priori when you test them, when you put it in an actual simulation and run wall-modeled LES, a lot of the times the results will change quite a bit, just because it's not trained actually on LES type flow fields. So again, those are some reasons that supervised learning might not be the most efficient way to do wall modeling. So then I'll move on to kind of our approach on how we do wall modeling, which is using reinforcement learning. I'll share some of our results, both on the flat plate case, the zero pressure gradient case, and the cases where we have pressure gradient effects. So if you remember the schematic for wall models, again, we have a core simulation grid where we take velocity information or flow information from an off-wall location. We plug that into the wall model, we get a wall shear stress, and then we apply it as a boundary condition. This schematic is very similar to how reinforcement learning actually works. So if you change your core simulation grid as your environment, the information that you're taking from the off-wall location as your state, your wall model is now your agent, and then the wall shear stress that you get out of it is now called an action. This is basically how reinforcement learning is trained. So on top of that, you just need a reward when you do the training. And the goal of, or the objective of the reinforcement learning is to find an optimal policy that maximizes the expected long-term reward. So basically you train it such that you're optimizing the long-term reward. The benefit, again, over supervised learning is that your environment, or your the grid that you're already learning from, is very much a well-modeled LES grid. It's not a direct numerical simulation grid, so you don't have to worry about this mismatch between those two and numerical errors that pile up. Again, also you're integrating over long periods of time to get the long-term reward, so there's going to be no mismatch between a priori and a posteriori testing. So let's look at all of these variables in one by one, and I'm going to explain to you how I chose all of these things for the reinforcement learning case. And for the first step, what we want to do is we want to make sure that this is a feasible thing to do. So instead of going into the complex physics, what we want to do is we want to stay with the zero pressure gradient case and make sure that this model works for that case, and then move on to more complex cases. So in this first part, you'll see the zero pressure gradient case, which is kind of a trivial case, mostly because the current wall models do so much better, but we want to make sure that reinforcement learning can kind of copy the performance of the current models. So let's look at them one by one. So the action, what we want to do is we want to use it as kind of a control parameter for this wall shear stress that you need out of the wall model. Reinforcement learning does best when it is a control policy. And it also works well because now you don't have to predict something that you don't know. You just need to know whether you should increase or decrease it. So what we do is the action, which is A, is going to act on our previous prediction of the wall shear stress and choose either to increase or decrease it at the next time step. So that's kind of what our action does. We've set some bounds for the actions, but once we've trained it, we've realized that these edge point cases are never really reached. So this is just a safety feature to make sure that things don't change too abruptly. But the idea is, again, to kind of turn this knob to either increase or decrease the wall shear stress. For the reward, we have this very long equation, but eventually you can actually just break it down into two parts and interpret each of them. So the first part here is explaining the improvement from the last step. So how much did our prediction improve compared to the last step? So tau wall is the true value, and this is taken from statistics. So we don't need full field data, we just need statistics. And this can be obtained either from experiments, from simulations, and easily obtainable through literature too. So we don't really need to run simulations. And then the tau wall M, this is the model prediction. So here you have the prediction at the current time step. This is a prediction error at the previous time step. So this first part shows you how much we improved our prediction compared to the last time step. We also have this bonus term, and this is because once you've improved enough that there's no more improvement that you can make. And we want to make sure that our prediction stays at the correct location. So we add a bonus if the error is less than 1%. So that's kind of how we set our reward. Was there a question?
Yes, ma'am. Sorry to interrupt. The previous thing, is that the iteration that you're talking about, the iteration and the error and the number of iterations and the solution converging, is this the...
Sorry, I don't think I understand the question.
Is this referring to the iteration, number of iterations and the solutions converging to accuracy, or?
No. This is just saying that at a given time step, how we obtain the reward for the system. So the reward is given based on how much we improved from the last step. Obviously, if we improved a lot, the reward is going to be high. If we didn't improve at all, or if we even gave a even wrong prediction, then the reward is going to be very low. So that's just because in reinforcement learning, what we're trying to do is we're trying to maximize the cumulative reward. Eventually, the policy that the model is gonna converge to is the case where the reward is maximized. But for now, we're just trying to figure out a good way to make sure that the model improves at each time step.
Thank you, ma'am.
Okay, and then for the states, we had some questions on how to choose the states, because this is kind of where it becomes very important what kind of information to feed into the flow. For that, we chose kind of two different approaches. First was kind of a very naive approach where we say, well, we know that this law of the wall exists, so we're gonna make sure that we take advantage of it. And the two variables that are plotted are basically the velocity and the wall normal location. So we say we're going to take those two as our state variables. All of them are normalized with modeled quantities, so we don't use the true quantities anywhere. And the idea is that if you have, for example, a point that is above this log law, this control setup is supposed to push this point down by increasing the wall shear stress, and then vice versa if it's below the log law. But the idea is that hopefully the model can learn to distinguish whether the action or whether we should increase the wall shear stress or whether we should decrease the wall shear stress. So that was kind of the first model. Again, this is kind of the more naive way of looking at the model. The second model, we also looked at the log law, but we decided that, can we take advantage of the fact that there are these two coefficients? The reason that these coefficients are important is because they're actually constants for the zero pressure gradient case. And it would be good if we can recover these constants somehow from the reinforcement learning. Again, remember the reinforcement learning never learns of these constants directly, like they're never fed these constants. So if we can somehow learn these constants, maybe that's like a better way of doing the training. So we look at this expression, we try to extract this 1 over kappa and b coefficients from just the instantaneous velocity data. And obviously instantaneously you would have a velocity and a velocity slope. And based on that, we tried to calculate this instantaneous equivalent of the coefficients to see if we can do something with that. Again, here, all of the information that's being fed in is instantaneous, based on instantaneous velocity gradients, wall normal locations, and so on. So there's no real information about this log law that is being fed in directly, at least, to this reinforcement learning process. And again, the idea is that somehow the model will learn that in these particular cases, we need to increase the wall shear stress, move that point down. If the point was already below the log law, we should try to decrease the wall shear stress so that we can move the point up, and so on and so forth. So that's kind of the idea in hoping how this reinforcement learning works. So let's see. So all of this is, kind of a summary of what I just said in terms of action, reward, and state that we chose for our model. For the training, because we're working with a zero pressure gradient case at first, we can do a very simple flow that is a channel flow. And that means that we have two kind of infinitely long parallel plates and flow is going through them. We use relatively low to moderate Reynolds numbers. So to train, we have a Reynolds number of 2,000, 4,000, and 8,000 that we're training. For the LES separate scale model, we're using a model called AMD, which you can find in this paper that's cited on the bottom left, Rosema Bay et al. And for the grid resolution, we're using about 10 points per boundary layer, which is very typical of wall-modeled LES. The code uses a second order finite difference scheme with the RK3 time stepping, along with the fractional step method for pressure, which is a pretty common code in fluids. In terms of the reinforcement learning details, we use a library called Smarties with VRacer, which is a off-policy training method that includes remember and forget experience replay. So this allows you to keep the relevant experiences from your training and then discard the ones that are not relevant. We've used RNNs with 2 hidden layers with 128 units each. We haven't really optimized in terms of the architecture for the neural nets, but this has worked relatively well. We also use a soft sign activation function for the neural nets. So what has the model learned? So this is once we've trained the model, we've looked at what we call the action state map. And this gives you a plot where the red means the action is to increase the wall shear stress, and the blue means the regions where action is to decrease the wall shear stress. And on the two axes, we have the two states that we've fed into the model. As you can see here, the model can distinguish regions where you should increase or decrease the wall shear stress very well. And in particular, the line that divides these two regions is the log law, so is the law of the wall. So somehow the model has learned that the distinguishing feature of whether you should increase or decrease your wall shear stress on average is this law of the wall. So it makes sense because the model somehow has learned this law of the wall through this reinforcement learning process without having this direct access to these modeling coefficients at all. So this is encouraging. At least a priori, it shows us that the model has learned the correct behavior, and we hope that this will show in the testing process. For the second model, we also observe the same, that the two kind of features are very distinct. It's a bit difficult to interpret in this case because we don't have that log law, but it seems like, you know, they are centered around the correct value of 1/kappa and V that we expect. So it seems that the model has learned something in terms of distinguishing when to increase or decrease the wall shear stress. So when to turn the knob to the left or to the right based on the flow states. So this again was very encouraging. So to test, what we did first was to test on channel flow case at higher Reynolds numbers that we've trained on. So ranging from 5,000 to 1 million. We use the same kind of details for the LES solver, and we test our wall model for this configuration. So here are the results. This is the error in the wall shear stress. On the x-axis, we have Reynolds number, and on the y-axis, we have the error of wall shear stress in percentages. What you see is kind of, you know, two different results. So remember, we had two models, one using kind of the naive formulation, the second one using the constants as kind of the training parameters. But the open circles are the ones that are the first model. So this is the first model, and this is the second model, and they show very different behaviors as you increase Reynolds number. So let's look at the first model and see why it behaves this way. So in our training process, basically we've trained on kind of low to moderate Reynolds numbers. And in that case, what we're training is in a range of Y's, Y pluses in this gray region. As we start increasing the Reynolds number while keeping the grid resolution the same, what we're essentially doing is that we're increasing the Y pluses that the model is seeing. As we all know, machine learning does very bad when it starts seeing data that it's never seen before. And that's basically what's happening here. So as you start increasing Reynolds number, more and more so the model is seeing values of Y that it's never seen before, and it just doesn't know what to do. There's one way to mitigate this, and that is to reduce the grid resolution. So refine the grid so that your testing and training data kind of line up in the same region in the flow. And that's what we did in this triangles here. So you can see that when you refine the grid, you see a much better prediction of the wall shear stress. In the first model, just because of this design in terms of the states where we use the U and the Y's as our state variables, we need to do grid refinement as we start increasing in Reynolds number. So this is not the most desirable trait of a model, even though it is usable in a way. So we're going to focus now on the second model. So now if we remove the results from the first model, we see that the second model also the error does increase with Reynolds number. At 1 million, we have about 4% error, which is, you know, not that bad, but also not great. But considering that this was kind of just a very naive approach in terms of training, we're pretty happy with it. And in terms of the RANS models that are used in the state-of-the-art sense, those results are down here. So it has maybe 1% error at 1 million, which is again much better. But then again, remember that in this case, they're tuned essentially to make sure that they have 0 error. This is what the mean velocity profile looks like. It should lie mostly on this black dashed line, that is the log law. And you can see that up to the 100,000 case, it does fairly well. And then you see the larger gap in the 1 million case. So again, it's not perfect, but we're pretty happy with where it was in terms of the channel case. We've also did a testing on the turbulent boundary layer. So this is a spatially evolving turbulent boundary layer with zero pressure gradients. The RE theta range for this simulation was between 1,000 and 7,000. And on top of the same LES details that we've used as before, we just include a recycling scheme for the inlet boundary condition. This is the result for the skin friction, which is kind of the same thing as the wall shear stress. So in the dashed line, we have the kind of empirical formula for the skin friction. And then in the circles, we have the reinforcement learning model. So again, the results match fairly well in terms of the prediction. And we were pretty happy with this result. And here are the mean profiles at different streamwise locations for the turbulent boundary layer. As you can see, they also lie quite well on the log layer, even though the Reynolds numbers are quite low. So we've mentioned that eventually we wanted to tackle flows with pressure gradient effects, mostly because that's kind of where these wall models will be used the most. So for that, we've extended kind of our training. We wanted a flow configuration where we had all the features that we wanted in a non-zero pressure gradient flow. So we chose this configuration called the flow over periodic hills, where we have a periodic domain in X and Z, and we have this bump that is repeated kind of infinitely many times, basically. The good thing about this geometry is that there's this favorable pressure gradient region right before the hill. We have an adverse pressure gradient region forming at the top of the hill, and then separation happening here right behind the hill. So it has a wide range of flow phenomena that is related to pressure gradient effects. And it was just a very simple case that we could run. So the idea is that we could train a model on this simple case and hopefully run on more complex models, such as a flow of an aircraft. So for that, we use the unstructured solver that is using finite volume. For the subgrid scale model, we use the dynamic Smagrinsky model. And the initial case that we've trained on is a Reynolds number based on the hill height of about 10,000. The grid resolution is quite coarse, again, very similar to what you would expect in a true wall modeled LES case. And basically, we've trained using the same details for the reinforcement learning library. Oops. I don't know. So again, same idea. We look at the reward state actions. Most of them stayed quite the same. So again, the action in this case is of a quantity called the wall eddy viscosity. It's a proxy for the wall shear stress. So pretty much very similar to what we did in the channel flow case. The reward stayed the same. Again, two parts. One is the improvement from the last step. The other part is the bonus if the error is less than 1%. And finally, the actions. We added one extra thing, that is the shear strain rate to our previous first model. We wanted to try the first model to see if it'll work first. And in this case, we added the shear strain rate because this is a quantity that will tell you relative to your streamwise upstream location, how the flow has changed. So we need that extra information to kind of capture information about pressure gradient flows. So these are our three states, and I'm going to show you some results now. So here are some results. It's a bit busy, but the DNS results are shown in these figures. So these black figures are your DNS. And this magenta line you see here is our state-of-the-art model. And you can see that it highly underpredicts the wall shear stress, especially near this favorable pressure gradient region. And here, if you look at this zero crossing line, you can see that the separation bubble is very, very small compared to what is predicted by this black line here. So again, these are expected that the equilibrium model deviates from the true flow when you have pressure gradient effects, and you can see that here. The other three lines, the blue, green, and red, are the reinforcement learning wall models for three different grid resolutions. And you can see that it does fairly well in predicting the the very large peak in skin friction when you have the favorable pressure gradient region. It does also very well in terms of predicting the separation bubble size. So this is a vast improvement to the equilibrium mole model, which, in a way is expected because this is kind of the case that we've trained on. This is the mean streamwise velocity and the stream functions that are plotted, which shows you the size of the separation bubble. And you can see here, this is the true result from well-resolved LES. You can see the separation bubble size here, which is quite similar to the separation bubble size you see in the two cases that use reinforcement learning. And then in the equilibrium mole model, you see that it is quite a bit smaller than the well-resolved LES case. So again, these two models do fairly well in terms of the separation bubble size prediction. I also wanted to show you the state action map for this case. So here what we did was we've chosen 3 locations in the streamwise direction and plotted the state and actions in all of these cases. Because we have an additional state, we have 2 plots for each location. You can see that for the green and the blue locations that these 2 figures, the red meaning to increase the wall shear stress and the blue meaning to decrease the wall shear stress, are very well separated, and they're separated by this mean profile that is obtained from the well-resolved LES. However, in the top of the hill, so in this red region, you can see that there's some mixing of these 2 quantities. And also the separation is not very well defined by the mean quantity. And this is actually where we expect the most deviance from well-modeled LES and DNS, just because the grid resolution just can't capture the very fine separation bubble that appears at the top of this hill. So in a way, it's a bit expected that the model doesn't do well there, but it's also good to see that the state action map can predict it in a way. We've also tested this in higher Reynolds numbers, and it seems like the model adapts quite well. So you can see that, again, regardless of this Reynolds number, which has doubled and quadrupled in each of these cases, you see a good prediction in the favorable pressure gradient region compared to the equilibrium mole model again. And then the separation bubble size is also pretty well predicted, although we don't really predict this secondary dip here. But if you just look at the 0 crossings, you can see that the size of the separation bubble is fairly well captured. So with that, I want to just summarize my talk. We've used multi-agent reinforcement learning to discover wall models for LES. This is a very data efficient way just because we only need statistics. Also, there's a direct coupling between the grid resolutions used in training versus testing. So we don't have to worry about this decoupling effect between LES and DNS results that a lot of the supervised learning models suffer from. The model was able to predict wall shear stress for a canonical channel and turbulent boundary layer flow. And we were pretty also happy with separated flows as well. We've extended the model to pressure gradient flows using the periodic hill configuration. We found that some formulation of the state space works better than others, so we're still working on kind of honing that in for the pressure gradient flow case. And finally, we would be trying to apply this to more complex geometry in the future to make sure that the model developed from canonical flows can be extended to complex geometry. So that's kind of where we're at this point in research. With that, I would like to thank everyone for your attention. I want to also point you to these 2 publications that I have for the zero pressure gradient boundary layer case, which was published in Nature Communications earlier this year. And then the periodic hill case, where we have a proceeding of the summer program from the CTR. This is uploaded to archive, so it's available now, but it'll appear in the proceedings later this year. And with that, I'll take any questions that you might have.
Oh, thanks for this very detailed presentation. So actually, I saw like everyone can ask a question, like just open your mic or you left the question in the chat. So I essentially saw someone already left a question in the chat.
Yeah, maybe I can read it. So, Kosher said, law of the wall is a steady phenomena. How do you impose a steady phenomena on an unsteady calculation? Did you perform average of your LES to bridge it to the law of the wall? Yeah, so that's true. It's an unsteady phenomena. Turbulence is an unsteady phenomena, but it is also a statistically steady phenomena, especially when you have a zero pressure gradient turbulent flow. So in a way, it's part of the model where you assume kind of using this steady phenomena to model unsteady phenomena. But at least for statistics, which a lot of the times what people are interested in, it seems to do fairly well. So if you look at mean velocity profiles, mean RMS profiles, and even spectra, using the law of the wall still gives you a pretty good answer. So that's kind of why we use that. You can also model the unsteady phenomena by looking at kind of the spread of the wall shear stress, and there are definitely models that take that into account. For the reinforcement learning model, it kind of automatically bakes that in a way, because this is a control strategy. You're not trying to match the correct wall shear stress at each time step. You're trying to just move towards it. So in a way, it's somehow baked into the model already. The unsteadiness actually becomes more important when you have a separated flow or when you have a pressure gradient driven flow. And we're still working on how to improve the model. But for now, the state of the art is using just the fixed law of the wall, and that's it. So again, there's a lot of improvement that we can do, but we're hoping to do it step by step.
Okay, thanks for the explanation. Is any other people has any other questions?
May I ask a question?
Sure.
Okay. Okay. Well, thanks for your nice talk. I have known how many iterations or episodes during the training in your introduced cases.
Yeah, that's a good question. So we did, if I remember correctly, we did about a million gradient steps. So that was about 1 week in terms of wall clock time. In terms of the number of simulation, we did, several simulations in parallel to do the training. I don't remember the exact CPU time, but it was about like 1 million gradient steps.
Yeah, okay, thank you. It's a long time.
Yeah.
Hello, I have a
Yep.
question. Can I ask?
Sure.
Hi, thanks for the very informative lecture on this turbulence modeling and simulations applied to the flows. I would like to ask whether any adaptive grids or any kind of boundary fitted grids was used during the simulation, because these grids are tailor-made to capture the effects of boundary layers flows, and at the same time it can also capture inherent boundary layer features like Blossius boundary layer and some inherent phenomenon associated with the boundary layer theory. So just out of curiosity, was any boundary fitted grid or body fitted grid or any kind of near wall adaptive grid or any kind of localized refinement near the wall, was it used in this case?
No, and I think the whole point of wall model LES is that you don't need to refine close to the wall. So here we assume that we have about like 5 to 10 points per boundary layer thickness. And that's kind of the minimum we can do, because if you don't have any points in the boundary layer, there's no way that you could predict the wall shear stress. So at the minimum, you need about 5 points per boundary layer. And that's kind of the assumption that we've used here. Now, if you go to a bluff body, flow over a bluff body or external aerodynamics or anything like that, you would need refinement close to the body, such that you have about 5 points per boundary layer. When you have a laminar region, that's going to be very difficult, and that's a whole different issue, because laminar to turbulent transition is something that modeling suffers a lot with. But once you have transitioned to turbulence, the idea is that you would ideally have about 5 points per boundary layer, and that would be enough to kind of predict the wall shear stress well.
Thank you. And just out of curiosity, hypothetically speaking, did you observe any case of divergence or any kind of non-convergence during your simulations, and how did you manage to solve it?
So we haven't seen that in this simulation, but also we've taken a lot of care in the initial conditions that we start our training processes with. So you need to feed in basically a wide variety of initial conditions, and once you've done that, hopefully the model has kind of capability to, push the flow towards the correct solution, basically.
Thank you. One last question. Will this informative lectures recording or the PowerPoint presentation, will it be shared with us?
Sorry, what was that?
Will the PowerPoint presentation or the recording of this lecture, will it be shared with us?
Hi, do you have an answer for that? My understanding is that this is recorded and should be available somehow.
You're muted, Kai. By the way, yes, this will be uploaded on our webpage or YouTube channel. You're muted, Kai. Kai, we cannot
Oh,
hear you.
yeah. Sorry. Oh, Giovanni, I saw your raise your hand. So yeah, just ask any question you want. Yeah.
May I ask one question,
Sure.
James? So if I well understood, concerning the Reynolds number, you train the model on a lower Reynolds number, and then you obtain, say, the wall shear stress for higher Reynolds number. Is that correct?
Yeah, so you have to devise the model well for it to be applicable to a wide range of Reynolds numbers. But if once you've done that, yes, the idea is that you can train on a lower Reynolds number and then test on a higher Reynolds number case.
Okay, and when you say train, you mean, I mean, in the slide saying this is data efficient, which basically use some statistics, the tau W is, as you said, is like statistics. But when you say training, you mean that you use DNS or LES field?
No. So
what do you mean with training?
Training is basically coming up with the reinforcement learning model.
Okay.
So yeah, so that's what I call training.
Yeah. Okay, so basically define the parameters. Okay. Yeah, that's true. Very quick one. So in one of your slides, when you have this contour plot, the blue and the red one, where you basically distinguish the 90% to 100. Yeah, you basically distinguish the line where you have.
Sorry.
Some kind
like
of
this one.
that one. Yeah, I was a bit surprised that you have this, concentrical plot contours, because I imagine if you go, say, very far from this expected line, you get darker and darker regions because you're very far from your, say, objective, while you, let's say, around U star 30 is kind of wide. Well, I could expect dark red. You know what I mean?
Yeah, so the part of that is that, the flow is being solved through a LES solver. So it's not like the flow solver itself is going to divert so far from the mean profile in a sense. So you're kind of dealing with values that are almost centered around this mean profile to begin with. So there are kind of no cases where you would see a very high value or a very low value in this case.
Okay, I see. Yeah. Thank you.
So Ali, I saw you raise your hand, so you can ask any question you want.
All right. Thank you, Professor Jain, for the nice presentation. I have a quick question. I'm a newbie to the reinforcement learning, and I wanted to ask, for this model being put on top of the CFT, which tool you were using? Either was it an open source framework or a commercial software?
Yeah, so it's an open source software called Smarties. It's available through a GitHub repository. and it has documentation. So this was developed from Petros Koumoutsakis's group, who's now at Harvard, but they have it open source. Yes.
All right, great, thank you.
So essentially, Professor Bei, I have a question like yeah, it's a quite short question. So if the it seems like all the reinforced model is firstly trained and then applied to the sort of the same case they were trained. Is this say for the real geometry, you probably don't have a simple after the hill or the TBL. Is this possible you trained in your one case and then you apply this to another case and it's still accurate?
Yeah, so well, for the flat plate case, we've trained on a channel and then tested on a turbulent boundary layer, which are technically two different flows. For the pressure gradient flow case, we are now currently looking at other geometries. So in particular, we're looking at a Boeing Gaussian bump and also looking at applying it to a practical aircraft as well. So the idea is that we've trained on lower Reynolds number, simple geometry, canonical flows, and that can be applied to higher Reynolds number, more complex geometries.
So how's the computational cost using the reinforcement model compared with say LES, or LES may be very long. So how is compared with runs as well?
Well, this is LES. It's not. I mean, it is LES. It's just using a wall model on top of LES. So if we compare it to the state-of-art wall modeled LES, it's actually cheaper just because we're evaluating a neural net compared to solving an ODE at each time step. So if we compare it with just typical wall model LES that's being used, it's significantly cheaper than that. Compared to RANS, maybe RANS is cheaper, but there's no way RANS can predict separated flows well. So I don't think that's a good comparison.
Okay, yeah, thanks. Is there any other questions? So it's also about the time. So thanks again for Dr. Bei to give us such a fantastic presentation, and thanks everyone for coming to the IBiM meeting. We'll see you next week. Bye.
Thank you. Thank you for having me.
Thank you. Cheers.